All right, so we're looking for the domain of these two functions, and they're kind of special, but it says without graphing. So I kind of want to talk about it, like talk about the values of x that we would have to throw away, and then kind of see if we can figure out what the domain is. And if we need to go ahead and sketch it, I've got some axes here that we can go ahead and do that. Or maybe we'll end up doing it just to help people understand why we chose the domain we did. But look at this first one. The square root of x squared minus 144. So I have the square root of a quadratic. Okay, now here's the thing. I'm looking for values of x that when I plug it into here, x squared minus 144, that's going to result in a positive number. I'm only wanting a positive, because what's going to happen if I get a negative? Someone said imaginary. Yes. If you try to take the square root of a negative number, remember that gives you the imaginary unit. So if it goes imaginary, that x is not part of my domain. Okay? So any ideas? Are there any numbers that we could kind of focus on to help me out here? I'm sorry? 12i? Oh, you're close. Just forget one little part of that. Just take the number. Just the 12. Now, 12i squared, I squared, do you remember what that is? Oh, it's negative 1. Okay, so 12i squared would be negative 12. So we kind of got those in an unusual way, but we do have 12 and negative 12. Why are 12 and negative 12 important to this radicand? Now, don't worry about the square root right now. We're only looking at x squared minus 144. It's difference of squares. When you factor it, you get conjugates, x plus 12, x minus 12. So, for example, if I were to plug 12 in here, 12 squared is 144, minus 144 is 0. Can I take the square root of 0? We can, because 0 times 0 is 0, right? So you can take the square root of 0. That is actually okay. So I'm going to go ahead and tell you that the domain here is everything from negative infinity to negative 12, bracket, union, 12 to infinity. Okay, and I already see some eyebrows kind of furrowing a little bit. So maybe it's a good idea. Let me go ahead and walk you through the graph. Okay. Now remember, don't worry about the square root. Just look at the x squared minus 144. Okay. What type of graph is he? Is he linear? Is he parabolic? Is he radical? Well, this is a radical. Remember, don't worry about the radical, just the radicand. The x squared minus 144. He's a quadratic, right? He's a parabola. Well, what direction would he open, up or down? Up, because the x squared is positive. In fact, the minus 144, what kind of transformation is that? It's just going to shift or pull everything down, right? So we're going to have a graph that looks something like this. And this is not going to be to scale. So this is negative 144. Now think about it. Where y is equal to 0 means the values of x that would force me to take the square root of 0, right? So what do you think this point is right here? That's negative what? 12. And this is 12. So see, that's why 12 and negative 12 were so important to the function. That's where he crosses the x-axis. So we've kind of talked on this idea before. If you're above the x-axis, that's where you're positive. That's where you have all your positive y values, right? What if you're below? You're negative. Well, take a look at the domain that I gave you. Everything from negative infinity to negative 12. So this represents this area right here. Okay. While the 12 to infinity is represented by this right here. You see, I didn't take any values of x between the two, because where's the graph? Sorry. So where's the graph between negative 12 and 12? It's negative, right? So see, think about this. If I were to put in whatever value of x this is right here, it would correspond to a negative y value. So that would force me to be imaginary. If I were to choose a value here, no matter what x less than 12, it's going to give me a negative, again, imaginary. Even 0 itself is giving me a negative 144, which again is going to go imaginary. So because it's a square root over this, any part of the graph that happens to be below, we want to eliminate those x's. So that whole interval between we have to throw out. But any value of x, like this one here, that would correspond to a positive y is what I want. Is everybody okay with that? Okay. Now here, number 2 is the same type of problem. Okay, but there's one difference. Let me go ahead and take a look. It says x plus 5 over the square root of x squared minus 4. So focus on the x squared minus 4. It's just like before. I only want values of x that are going to result in x squared minus 4 being a positive number. No negatives, because we don't want imaginary. Does anybody know 2 particular values that would probably stand out? Negative 2 and 2. Why are those important? Okay, it's a difference of squares, just like the previous one. In fact, that's where x squared minus 4 would cross the x-axis. So does anybody think they know what the domain would be? Okay, so negative infinity to negative 2. Negative time to bracket, okay. Union 2 with bracket to infinity. Now, I'll tell you, you're spot on with your form. There's just one detail that's different from number 1. Why shouldn't it be a bracket? Now, think about it. Where's the radical this time? It's on the bottom. It's in the denominator. So we just said a second ago, we can take the square root of 0 and get 0, right? Okay. But because the radical is in the denominator, we can't include that because we would be forced to divide by what? 0. So at negative 2 and 2, the function would be undefined. See, we could go ahead and include the 12 and negative 12 in number 1 because we're not dividing by 0. We can take the square root of 0. But in number 2, we can't do that. Is everybody okay with that? Okay. All right. Good, 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 good. Now, we'll probably go ahead and get started with the, definitely get the vocabulary out of the way. If you want to go ahead and turn in your focus activities today and just be done with it, I'm looking for numbers 4, 5, and 6 is what we're going to turn in. But we're going to turn it in at the end. Okay? We'll turn it in at the end. All right. Let's talk about some inverse functions. This will be what we discussed this week. We'll do some factoring next week, and then we'll finally be able to move on to trigonometry, the sine, cosine, or what you learned in geometry, SOHCAHTOA. And we'll be able to go on with some other stuff too. All right. So let's see here. Graphs of inverse functions are reflections in the line. So looking at this graph over here, what's the line we reflected one of them over? Y equals x. It's the linear parent, yeah. If you want to find the inverse graph, okay, for any function, all we need to do is reflect it across y equals x. That's my line of symmetry. Okay? Now, given a function f of x, the notation for the inverse function is what? Now, if someone were to look at my paper, how do we write an inverse to let them know we're referring to an inverse? Oh, you're on the right track. What's that, Nathan? The negative 1 is spot on, but we don't use y. We use that function notation. So if we have f of x, we say f inverse of x, or the inverse of x. Okay, very, very important. That negative 1 is not a power. That's just the way we write an inverse. And the same can be done for any other function we come across. We could say g inverse of x, k inverse of x, for whatever variable you're given. Okay, that does not matter. Okay, the domain of a function is equal to the blank of the inverse. The range, yes. So the range of a function is equal to the domain of the inverse function. Okay. So if xy is a point on a function, then blank is a point on the inverse. Yx. When you reflect across this line y equals x, all you're doing is reversing those values. Now, you're not changing their sign. A lot of people are tempted to do that. Let's say you have on f of x the point -1, 2 on the inverse. Okay. Is everything good?
Yeah.
You okay? She's just super excited to be here. There you go. All right, so what would it be on the inverse? 2, -1. The signs don't change. You simply switch the values. And that's the core idea when it comes to dealing with inverses. You're going to take all the elements in your domain, okay, the x's, all the elements in the range, your y values, and you're simply going to switch them. The x's become the y values and vice versa. Okay, now when you start looking at the functions, whatever you're going to notice in the function, whatever operation, the inverse is always going to have the opposite operation. So for example, if a function is adding 2, then the inverse is going to be subtracting 2. If a function is multiplying by 5, then the inverse should be dividing by 5. Now, depending on the function, it may be really easy to see those directly, but if you simplify sometimes, that may not be as obvious. But it should be performing the opposite operation. Okay. To verify algebraically that functions are inverses of each other, you must show that. Does anybody remember this? And this is why we did the previous lesson over compositions. Okay, we got to do this. F of f inverse of x would equal x. I need to be able, you remember when we were taking equations and plugging those into another equation? Okay, if I can plug one function into the other and it simplifies to x, this is going to tell me they're inverses of each other. But it's not just one way. It has to be able to work both ways. So see, here's f of f inverse. It also has to work for f inverse of f. Okay. And is it possible for it to work one way but not the other? Yes, it absolutely is. So you want to make sure you are testing both ways. If you test one and it works, I mean, it's looking good, but that doesn't guarantee that it's going to work the other direction. Okay. If a relation and its inverse are both functions, then both functions are, and even very few people in pre-cal IS got this one. Okay. No, we use this when dealing with the horizontal line test. It's just a little phrase. Has anybody ever heard of the horizontal line test before? So a few folks, okay. Yeah, you'll probably, hopefully recognize it. If not, that's okay. We call this one-to-one. Does that sound familiar? Okay. One-to-one is always hooked with what we call the horizontal line test. And I'll show you what that means in just a second. All right, so one-to-one. And then we have our last blanks here. If each value of the dependent variable and which one's always the dependent? The y. Okay, so the y variable corresponds to exactly one of the independent variable. That means it passes the horizontal line test. Then the function is said to be one-to-one. Okay, and that's one thing about inverses. We really, really like our inverses to be functions. That means that no value of x can what? Repeat. All the values of x have to be different, and that's what the vertical line test shows me. So if I were to give you an example, like let's say this guy right here. Let's just go with a general parabola. Okay. Now, let me go ahead and get a vertical, let me get a horizontal, and let me go ahead and do this with the mouse because it's going to work way better than the screen. Now keep in mind, I'm not the best artist in the world. I know it sounds kind of sketchy. Sketchy, it's funny, it's a drawing pun. Okay. But if I take this vertical line and I go ahead and move it back and forth, is he a function? Yes, he passes, right? Because you're looking to see if your graph hits the line in 2 or more places at once. That tells you if any value of x repeats, right? So this guy is a function. But what we really want to know is if they're one-to-one. This is when you use the horizontal line test. Now, if the vertical line test tells you if any x's repeat, then the horizontal line test tells you what? If any y's repeat. So does he pass the horizontal line test? No, it's just like the vertical, it's just horizontal. He can't touch it in 2 or more places at once. So this guy right here, he's not one-to-one. Now, why would that be important for us to know if we're looking at inverses? Remember, what did I say we do with the x's and the y's? We switch them, right? So if this guy has repeating y values and I find the inverse, then those repeating y's will become repeating x's. So I can already guarantee that this guy here, whatever his inverse is, will not be a function. And that's really important to us. We want those inverses to be functions. Okay. So I'll tell you what, we'll go ahead and stop there because I think we got decently far. We'll pick this up again tomorrow. And the next 2 days, we should be able to wrap it up. And then on Friday, we'll take our district assessment.